This video is on waves, specifically electromagnetic waves. So we're going to be talking about how energy moves, how it's related to electrons, but we got to start with that energy travels through space by electromagnetic radiation. So this is just talking about all the different types of waves based on the different energies and wavelengths and frequencies they have that would kind of exist in our universe. So all electromagnetic radiation is transmitted by waves. And you can see you've got a picture in your notes, and I've got the same picture here of all the different types of electromagnetic radiation. So obviously yours isn't in color. So I think you should go and add in the colors. You don't have to color this. I mean, you can if you really want to, but right, the colors in rainbow order are Roy, right, G, Viv. So we've got red, orange, yellow, green, blue, indigo. Indigo is kind of a in between blue, purple, and then violet. All right, so the electromagnetic spectrum goes from lowest energy on the left to highest energy on the right. So the energy increases left to right. So low energy waves are radio waves, microwaves, okay, infrared waves. So a lot of times, so this is all radiation. People will say, like, oh, all radiation is really dangerous. Well, no, not at all. Not all of it is. Microwaves are fine. Radio waves are fine. They're very low energy. Infrared, notice how it says infrared, and then what color comes next? Red. So this right here is the visible light. This is the only part of this whole spectrum that we can see. So only part we can see is this little teeny spot right here. This is the visible light. We can't see infrared unless it has some visible light in it. Just like we can't see the next highest energy, right after violet comes ultraviolet. We can't see ultraviolet or UV or black light unless they add some actual violet or colored light to it for us to see it. So like if I had ultraviolet without any, or UV without any other visible light in it, you wouldn't be able to tell if that light was on or not. All right, so from ultraviolet up, we start to get into higher energy, which can actually be a little dangerous, right? You get ultraviolet rays from the sun. This can cause skin cancer. X-rays, there's a reason you don't want to have X-rays every day or even necessarily every year, every month, and why we take precautions when we do have them. And gamma rays are the highest energy. These are the most dangerous that can come from things like nuclear radiation and such, which may be a part of medical stuff too when it comes to cancer treatments and things. All right, so energy increases left to right. All right, so now let's talk about what else changes from left to right, like for each wave. You can see I've got in the drawing, you can see the waves here, right? Do you see how they're getting closer together? All right, that's what we call the wavelength. It's the length of a wave distance from here to here. So like a top to a top, crest to crest, or trough to trough. This would be the same, okay? The other thing is frequency. So let's write these down. So parts of a wave. Wavelength is the distance between two consecutive peaks or troughs. So that's like from here to the next one. That's the length of a wave. Make sure, remember, you're pausing to write that down. The unit is a distance, a length unit. So it could be something like meters, right? When we have these really big waves over here, you're going to have meters. As they get smaller, you can see how they're getting closer together. We're going to go in smaller units. So it could be centimeters, it could be millimeters. And a lot of these waves are really, really, really small. So we're going to use units like nanometers. A nanometer, so a millimeter is 1,000. There's a 1,000 millimeters in a meter. There's 1 times 10 to the 9th nanometers in a meter. So they're much smaller. All right, frequency is, I mean, when you talk, just hear the word frequency, it's right, it's just how often something happens. So this is the same thing with waves. How often the waves. So the number of waves that pass through a given point per second. So it's waves per second. right? Just like you would do miles per hour. Like if we're talking about a speed, we're talking about how many waves per second. So our unit, waves is just gonna be a number. So our unit might be where we just write like per second, or even like 1/seconds as the unit, and we can just write S for seconds. And this is equivalent to, sometimes instead of writing per second or 1/second, we call this a hertz. Okay, so frequency is as these waves pass through a point, how many waves pass this point in a second? All right, so all of this is related to speed, okay? So wavelength and frequency, if you multiply these two, okay, your wavelength units are meters, let's say. Your frequency units are per second. Think about what you get there. Nothing cancels. You still have meters in the numerator, seconds in the denominator, and you get a meters per second. That's a speed unit. So we can have an equation for this to solve for this. The symbol we use for wavelength, I know you probably want to use a W, but it's this Greek letter lambda. Frequency is the Greek letter nu. And speed, all of these waves have the same speed. So all electromagnetic radiation has a, let me go back here. Travels at the speed of light. And the speed of light, we use the letter C for the speed of light, and it's 3 times 10 to the 8th meters per second. So light will travel 300 million meters every second. So when it comes to our equation, speed, all these are traveling at the speed of light, we're going to use C equals wavelength times frequency. So this equation is very important, as is what C equals our speed of light. So let's use these in a problem. So it says a student's listening to an FM radio station. Remember, radio waves are electromagnetic radiation. So the radio station, say, is B96. While they're doing their chem, the radio station has a frequency. Notice B96. So like on the dial, it used to be an actual dial, now it's digital, right? Here's 96. That's the number times 10 to the 7th for the hertz. That's the frequency. Okay, if radio waves travel at the speed of light, what's the wavelength? So let's figure out what we know and what we're trying to find. So we know the frequency. It tells me that I have 9.63 times 10 to the 7th hertz. Remember, hertz is 1/seconds, and I'm going to write it like that. It says if radio waves travel at the speed of light, well, that's that C, and it's just 3 times 10 to the 8th. So you'll be given that. You just have to know what to do with it. And then what's the wavelength? Right? So I figure out what I knew and what I was trying to find. So my equation is, right, C equals wavelength times frequency. And so now we want to solve for wavelength, that lambda there. So we got to do the algebra. We have to move frequency over. So if I divide by frequency on both sides, right, we know this divides out then. So my wavelength equals, because I like to go left to right, I'm just going to flip these two, speed of light over frequency. And now I can just plug in my values. So the speed of light is 3 times 10 to the 8th meters per second. My frequency is 9.63 times 10 to the 7th, 1/seconds. So unit-wise, per second on the top and the bottom divides out. And remember, when you're typing this in your calculator, that you're using your scientific notation button, whatever that may be on your calculator. So I'm going to round this just to 2 numbers after the decimal. Make sure you type this in and you can get this. So I get 3.12. Meters is what didn't cancel out, so my unit is meters. And think about, does that make sense if I'm talking about wavelength? Yes, it does, right? Meters is a wavelength unit. So these waves, if you're listening to that radio station, are just over 3 meters long. Excuse me.